Okay, so we recorded these properties at the beginning of class, hopefully to help you figure out your lab, and hopefully we're able to see some of the patterns in these substances and the pH and properties that corresponded to acids and bases. The other part of the page I want you to fill in is about buffers. So we do not go very in depth with buffers in this class. If you take AP Chem, you will go a lot more in depth in buffers, in regards to buffers, okay? In this class, all I want you to know is that a buffer is a solution that resists changes in pH. Okay, it resists changes in pH. That means when small amounts of acid or base are added, the buffer helps keep the solution within a range of pH, keeps it from going too far away from the pH that it was at, okay? A great example of a buffer in our own bodies is our blood, okay? Our blood works as a great buffer because our blood likes to stay at a pH around 7.4. If it deviates outside of that, then you start running into problems, okay? Like life-threatening problems. So it's really good that our blood buffers our bodies because we do take in a lot of different substances on a day-to-day basis. We consume, in fact, a lot of acids like juices and fruits and things like that. Those are acidic in nature, but it is okay because our blood buffers our pH. So it's great. There's other examples of buffers. The ocean actually kind of buffers itself a little bit, and with a bicarbonate buffer, which is kind of similar to what our blood does. And if you take AP Chem, you'll learn a lot more about buffers. But this is what I want you to know for advanced chem, that it just is a solution that resists changes in pH. Okay? Any questions there? Cool. Then the next page, we are going to talk about amphiprotic, polyprotic, and monoprotic acids, okay? So amphiprotic, these are going to be specific substances. We've actually already talked a little bit about one specific amphiprotic substance, but does anybody know what amphi means, that prefix? Both, absolutely. Amphi means both. So if you familiar with the term amphibian, okay, amphibians are organisms that can live in both aquatic and terrestrial environments. They go in the water and they go on land, like frogs and stuff, and salamanders, okay? Amphi means both. And protic here is going to refer to proton, okay? So when we talk about amphiprotic substances in chemistry, we are talking about substances that can act as either an acid or a base. We already talked about one of these with Bronsted-Lowry theory. We said based on what water is paired up with, water can act as either an acid or a base. It is the most common amphiprotic substance, especially as we deal with in this class. So this is based on that Bronsted-Lowry theory, okay? This was the donating protons and the accepting protons. Remember that in Bronsted-Lowry theory, an acid, do y'all remember if it donates or accepts a proton? Donates, yes. So an acid donates a proton. A base in Bronsted-Lowry theory, I'm just going to write donate again. That is not it. It accepts a proton, okay? So I know it's been a little bit since we talked about Bronsted-Lowry theory, been a couple class periods. But that is Bronsted-Lowry theory, very useful when identifying whether or not substances are amphiprotic. So here in this example, we have water doing its thing, acting amphiprotic, and we are trying to figure out, okay, are we behaving like an acid or are we behaving like a base here, okay? So if it helped you when we were doing those Bronsted-Lowry examples, if it helps you to draw yourself little arrows showing which thing is partnered with which, which thing becomes which, I think you should do that if that's something that helps you, okay? So our H2O to H3O plus, is water in this scenario, is it accepting a hydrogen ion, or is it donating a hydrogen ion? It is accepting, right? So it is. It is indeed. It's a base, since it is accepting. Okay? A base accepts a hydrogen ion. So what would that make H3O plus on the other side? Do y'all remember? Yes, very good. The conjugate acid. So if water is the base, what is HCl? It's the acid, and that makes sense because if we look at HCl going from here to here, what's happening to the hydrogen on HCl? Yeah, it's losing, or it donates it basically. So it donates the H plus. Okay? So this guy lost or donated the H plus, so that is going to be an acid. Okay? And so this guy over here, of course, is our conjugate base, because they're in pairs, right? Base and conjugate acid, and acid and conjugate base. Okay, flashback to bronchodilatry. See if y'all can do that for this example, okay? Draw your arrows, label your things. Okay, what do we think with water here? What is water doing here, y'all? It's losing. We lose the hydrogen ion, so what does that make water in this scenario? An acid. If it loses or donates its hydrogen ion, then it's an acid. And so over here, the OH would be the conjugate base, of course, yes. And so then we just fill in this guy, base and conjugate acid. But you could double check yourself and see that yes, NH3 is indeed accepting a hydrogen ion. So yes, it must be the base in this scenario. Okay? Again, you have to compare your sides. If it helps you to draw those arrows, do that. Any questions there? Again, water is famously amphiprotic. It can accept or donate a hydrogen ion based on whatever it's paired up with or whatever it's, hanging out with in the reactant side. Okay. Down here, circle the amphiprotic substances in the following reactions. Indicate in which reaction the substance is acting as a base and in which it is acting as an acid. So again, I just want you to do that similar situation. Identify acid and base. Figure out who is amphiprotic. You don't even have to, you can circle them if you want, or you can list them out. I like to list them out over on the side and say, this and this are amphiprotics. There's two that are amphiprotic. Figure those out real quick. Okay, what do we think, y'all? HPO4 negative 2. What is this? Acid, which makes water our base. Awesome. So over here, PO4 negative 3 is conjugate base. That leaves our conjugate acid. Very good. Okay. And then in this one, HPO4 negative 2 is acting as what, y'all? A base. Which means this is our acid, conjugate base, right? So which two substances are amphiprotic? One of them we obviously know we did in the previous example. Water. Water is, of course, amphiprotic here. What else is amphiprotic here? HPO4 negative 2. Very good. These are both amphiprotic. Okay. Cool. So those are some amphiprotic substances and how you could figure that out by using Bronsted-Lowry theory. Any questions there before we talk about mono versus polyprotic? Okay, well, what does the prefix mono mean, y'all? One. What does the prefix poly mean? Many, or more than one, right? Awesome. So, a monoprotic acid is going to be an acid that only has one hydrogen ion that can be donated, whereas a polyprotic acid, these guys have more than one hydrogen ion to donate. And fun thing about polyprotic acid are they can have forms that are amphiprotic. So, polyprotic, more than one hydrogen ion to donate. This is not going to be polyprotic. This guy is going to be monoprotic because there's only one hydrogen ion. This guy here, this is going to be polyprotic, okay? Polyprotic because there are two H's here. We can lose one and then we can lose the other. What about chloric acid, y'all? No, that is not polyprotic. There's only one hydrogen ion to donate. What about carbonic acid? Yes. How can you tell? There's two hydrogen. Beautiful. That is polyprotic. What about this last one? It's weird, right? If you're looking at acetic acid, you are only going to look at that first hydrogen, because remember, this guy is made up of the hydrogen ion and the acetate ion, okay? It's not going to dissociate into, carbons, hydrogens, and oxygens. It's going to dissociate into the hydrogen ion and the acetate ion. So there's one hydrogen ion to give it away. This guy is monoprotic. Do not let that trick you on a progress check or an assessment. This is monoprotic. Okay. Any questions there? So these are the only two polyprotic here. The rest of these are monoprotic. Here, I'm going to write in, again, for the sake of time, we kind of have a lot to get through today. I want to write in that this guy is amphiprotic. This guy is amphiprotic. And then this guy is polyprotic, and monoprotic here. Okay. So these two are amphiprotic. I want you to see if we have some kind of situation where these guys are lined up like this with these little back and forth arrows, these two-way arrows here. This HPO4 minus 2, this guy can accept a hydrogen ion and become H2PO4 minus 1, or we see if it goes this way, we can lose the hydrogen ion. So it's acting as an acid if we lose the hydrogen ion. It's acting as a base if we gain. Okay, same thing this guy. Acting as a base if we gain, just froze. Acting as a base if we gain the hydrogen ion. Acting as an acid if we lose the hydrogen ion. Okay, so these two are amphiprotic. We cannot say that these are amphiprotic because I do not see this guy losing a hydrogen, and I don't see this guy gaining another hydrogen over here. So I can't say that this or this is amphiprotic. Only these two. Any questions there? Cool. So we're going to review dissociation of acids and bases, and then I'm going to give you one more new thing to think about in terms of the amine bases. This is a little bit of a review because we did talk about dissociation and dissolving last unit. We did talk about acids and bases dissolving and dissociating. As a reminder, acids and bases do dissociate just like ionic compounds do. Remember that strong acids and bases will completely dissociate. Do y'all remember what type of arrow we used to represent the complete dissociation? One-way arrow. Completely dissociate, we use a one-way arrow. And so these guys, since they completely dissociate, they're going to form lots of ions. And so their pH and POH values tend to be on the more extreme ends of the scale. You may have noticed in your acid-base properties lab today that the KOH and the, what else did you have? I think you had sodium hydroxide as well. NaOH, those guys had higher pHs, more closer to 14, than a weak base like ammonia does, which was one of the other bases you tested. Okay? That's because they're strong bases. Okay? Strong acids and bases, they have more extreme pH values. Higher if it's a base, lower if it's an acid. Okay? So those are our strong acids and bases. The weak acids and bases, on the other hand, okay, weak acids and bases, these guys only partially dissociate. So that's the other arrow we learned about, the two-way arrows. Again, I don't care how you draw them as long as I see that they are two-way. One of those three will suffice. And so these guys only partially dissociate. That means less than 100%. Most times, less than 10%, okay? So we show these with a double arrow, and since they don't form as many ions when they dissolve, their pH and their POH values tend to be closer to the center of the scale, meaning closer to neutral, less extreme pHs. Okay? So just something to keep in mind. As a reminder, you still need to have your strong acids and your strong bases memorized. So hopefully you had those memorized last unit, so that's not extra work this unit. Remember my memory device for your bases, they are strong if you have an OH, and it is partnered up with a metal from the first two columns that are not magnesium and beryllium. So if it's any one of those metals in the first two columns partnered with OH, then it's a strong base. Everything else is a weak base. For the acids, if you remember, so I bring no clean clown clothes. Again, I know that's my really weird. I actually changed it from brought to bring because brought, brought was getting people confused with the bromic and the BRO3s. Yeah. So BR, just to remind you that it's just hydrobromic, not, bromic acid. So, sulfuric acid, hydroiodic, hydrobromic, nitric, hydrochloric. You have your chloric, and then you have your perchloric acid. Okay? So those are your strong acids. And remember that strong acids and bases are strong/good conductors of electricity, meaning they're strong electrolytes, while weak acids and bases are weak or poor conductors of electricity. They are weak electrolytes. So we already discussed these last unit. So hopefully you remember this from the previous unit. You do need to continue to know how to do these things going forward. And as we introduced a little bit earlier in this unit, we do have some weird, funky bases called amine bases, okay? So we have these things called amine bases. I'm going to introduce something to you today that is an addition to your dissolving equation process. For the funky nitrogen bases, or the amine bases as we call them, you must show water if you are asked to write out the dissolving or dissociation equation, okay? This dissolving dissociation equation will not work if you leave out the water for the amine bases, okay? So I'm not going to go through and write the dissociation equations for all these acids. You should know how to do that already. What I am going to do is I'm going to remind you that a basic dissociation equation, as we learned how to draw last unit, that will include, of course, the compound we are looking at dissolving. This is a strong base. This will completely dissociate. So we're going to give it a one-way arrow. When you write out your dissociation equations, you want to make sure you include the charge and the state for each ion. Okay, this guy also is made up of one barium ion and two hydroxide ions. So we want to make sure that we also put a 2 coefficient there to show that for every one of these that dissolve, we get 1 barium ion and 2 hydroxide ion out of it. And this completely dissociates. So we learned how to do this last unit with our strong bases. If you have an amine base, something like aniline, which we gave you the formula for that, you are not expected to memorize the formula for aniline or trimethylamine, for example. Aniline here, in order to write out this dissociation equation, you're going to have to include water as a reactant. It will not work if you do not include water as a reactant. And here I'm going to do a 2-way arrow because since it is not one of my metals in the first 2 column with OH, it is a weak base. So this is going to work very similar to, it's going to look very similar to the Bronsted-Lowry equations we were analyzing a couple class periods ago, because what's going to happen is this is the base, this aniline, this amine base here. This base is going to accept a hydrogen from water, and water is, of course, going to lose a hydrogen because it's donating it to this. So what we end up with is C6H5NH3. It gains a hydrogen ion, and since it gained a hydrogen ion, it's going to have a +1 charge now. It's going to have an excess of +1, +1. And the water, of course, that has donated the hydrogen ion is going to look like this. So there's how you get the OH for the nitrogen, the amine bases. That's how you get the OH for the amine bases. You have to include water over here or this is not going to work. It's going to be a real unbalanced looking equation. Okay? Again, for the sake of time, I'm just going to include this as well. So here's how this guy would look if you included water. I know it's a little bit weird because there's no H here. You're like, where do I add it? Do I add it right here? No. Remember, for your amine bases, you always add the H after the N. Okay? So what's that charge going to be now, y'all? +1. Yeah, it will be. It will be +1. And then you'll have the OH. Okay? That is how you write a dissociation equation for an amine base. You must include water as a reactant. Okay. Are we with it so far? Yes. An amine base, those are our bases that end in like N or NH, like this. Like ammonia is an amine base, NH3 is an amine base. Those things that contain nitrogen. Yeah. Any other questions? Okay, so what I'm going to teach you how to do next are strong acid and base calculations, okay? Remember, in strong acids and bases, 100% of the original acid or base will split into ions. This is for strong acids and strong bases. This helps us because it means we can use mole-to-mole ratios to help us calculate things like pH if we are given the molarity of a strong acid or a strong base, for instance. Okay? So we're going to be completing two types of calculations. Molarity of an acid or base is given, we need to find pH, pOH, or the pH and pOH is given and we need to find molarity of the acid or base. We will probably get through 2 calculations today, and then I will do 2 other example calculations with this second bullet point example, okay? So, what we are going to use for these is something called a Rice table, okay? Rice is short for reaction, initial concentration, change in concentration, and ending concentration. Okay? So you write out the reaction, which is going to be your dissolving equation. This is why we need to still know how to write dissociation equations, because that's going to be the R. The initial concentration is what we start off with, The change in concentration is how it's going to change, and this is real easy for strong acids and strong bases. Y'all are lucky because the past couple of years we have not made advanced chem do weak acid, weak base calculations, and those are the harder ones. The strong acid, strong base calculations are fairly straightforward. If you do take AP Chem though, Miss Marusik will teach you how to do weak acid, weak base calculations. And then you figure out your ending concentration and can use it to calculate things like pH. And then other times you can work backwards. So we're going to do an example with an acid and an example with a base first. Okay. For this first one, I'm just going to write this out so it's hopefully kind of a learning as we do situation. So we're going to write rice, R-I-C-E. And I want you to make sure that you show your work in a rice table because you will get points for showing your work in a rice table. So this is another situation where you can get partial credit. So please show your work. Bless you. So R stands for reaction. We're going to write the dissolving equation for chloric acid. I'm going to assume you know how to write a dissolving equation at this point, and I'm going to write it out for us so we can talk about what we're going to do with it. That is the dissolving equation for chloric acid. We are told that the concentration of the chloric acid is 0.05 molar. Bless you. We want to know what is the pH, okay? What is the pH of this concentration? So what we're going to have to do is we're going to have to use this information. We are starting with a concentration of chloric acid. Our initial concentration of chloric acid is 0.0500 molar. Okay? That is our initial concentration of chloric acid. And our initial concentration of hydrogen ion and chlorate ions is going to be 0. Because at this point we're looking at initial, we're looking at before this has dissociated. Okay? So if we're looking at chloric acid before it has dissociated, then we're assuming that this concentration is 0. The change in concentration, we're going to write how this concentration is going to change. Since this is a strong acid, forgot the A. Since this is a strong acid, and we drew the one-way arrow, that means all of this is going to break into hydrogen and chlorate ions. That means this concentration is going to change by the same amount as we started with because all of it is going to dissolve. Okay? If you think about this too, when we go right over here, what is happening is you're taking some HClO3, you're putting it into a solution. When you put this into a solution, okay, you're going to form hydrogen ions and chlorate ions, okay? That's what we wrote in our dissolving equation. For every one of these, we are going to form one hydrogen ion and we're going to form one chlorate ion. So the corresponding increase in concentration for each of these, since we have one of each of these, is going to be plus this concentration. Okay? Remember, each one of these is going to break into one of these and one of these. So these are each going to increase in concentration by the same value. And so the ending concentration is going to be 0 here. Again, this completely split into all of these ions, so we have none left in this form. And our final concentration here for these guys is going to be this. And we did this because what we can do here is once we know the concentration of hydrogen ion, we can use it to calculate the pH. Because remember, the concentration of the hydrogen ion, if you take the negative log, if you watched your video last class, you learned that the negative log of the hydrogen ion is equal to pH. So if you type that into your calculator, you would get a pH value of 1.3. Okay? See, there's our pH. Negative log of that value, 1.3. Yeah. Okay? And you might be thinking at this point, okay, why didn't I just take this initial value and then just plug it in there? Because that seems like a lot of extra work to just get the same number. You will not always have a 1-to-1 ratio, is the issue. And you are also not always going to be given an acid. Sometimes you're given a base. So this was like the most simple of calculations you could possibly do, okay? With something like this. Okay? What I want to do with you real quick before we end today is I want to do this base calculation, and then I'll finish recording the video with the 2 more example calculations, so you have a chance to watch those, and then you can ask me any questions you might have about those next time. Okay? So last calculation, we're going to do one more rice table. Again, I'm going to assume you know how to write out a dissolving equation. So here's calcium hydroxide. Yes, you still need to know how to write formulas. We've been doing that all year. We're going to get calcium ions and 2 hydroxide ions for every 1 calcium hydroxide that dissociates. So here we're asking what is the pH of this molarity calcium hydroxide. Well, that means we're starting out with that molarity, assuming that we haven't dissolved anything yet. That's going to be a 0, 0. 0 initial concentration. When this dissolves, since it is a strong base, it's going to completely dissociate. That means this is going to change by this much, same amount, because it's going to completely dissociate. The calcium, we have 1 calcium, so this is going to increase by that much. We have 2 hydroxide. So for every 1 of these that splits apart, we're going to get 1 calcium, and we're going to get 2 hydroxide ions. So here we're going to have to do plus 2 times this to get our final, okay? Because it's a 1-to-2 ratio. So twice as much concentration of hydroxide compared to the amount of calcium hydroxide we put in, basically. So that's going to be a 0. This is going to increase to this amount. And then this 2 times 0.0682 is going to be, oops, sorry guys, 0.1364 molarity. Okay? And again, we're looking for the pH here, so it's going to be a little bit weird because we were not given the concentration of hydrogen ions, but you did learn that you can get to pH from the concentration of hydroxide last class actually. If you take this value, which is your concentration of your hydroxide, you can calculate the pOH negative log of this gets you the pOH. 0.865 is going to be your pOH. If you type that into your calculator, again, I'm just kind of doing this quickly since we're running short on time. Type that into your calculator, you will get this. And then you know that 14 minus pOH is pH. So if you do 14 minus this, you can get the pH, which should be 13 point. Again, if we're just doing 3 sig figs. 13.1 here. Okay? So that is where we're going to end today. Again, I will do 2 more examples from the last page. So you have examples of how to plug things in going backwards. Please make sure you do your progress check, y'all. Okay, let's go ahead and finish up a couple more of these problems so you know how to do the rest of the types of problems that we have here for you this unit. I'm going to go ahead and give you the answer to this one, example 22, since you should know how to do this one now. I just want to make sure you're able to check your work. The answer to this, you should get a pH of 12.8. So you can do your work and check it against this value. The other types of problems I want you to be familiar with doing are when you are given the pH, for example, of a solution. I want you to know how to go backwards and get the concentration of the acid to start with. And, and here we have another answer that you should be able to figure out. You should be able to figure this one out. Okay, pH for that one should be that value. Okay, so example 24. If the pH of hydrobromic acid solution is 3.20, what was the molar concentration of the acid to start with? So in this type of problem, we are given the pH and we have to figure out the molar concentration of this acid. So we don't know what the molarity is, but we're trying to figure it out. So you are going to still use a rice table, but you're going to have to kind of work backwards from the process that we were doing. So over here, we were given the pH, not the pH. We were given the concentration. We plugged it into the rice table, and then we found our concentration of our hydrogen ion here, and we were able to use that to solve for the pH. Or we got the OH, the concentration of the hydroxide, and then we did a little work to find the pH in this case. Well, here we are given, of course, the pH to start with. So we're going to use this since we have an acid solution. This is HBr. We can use this to figure out the concentration of hydrogen ions that we would get from hydrobromic acid, and we can work backwards plugging things into a rice table. So we're going to go ahead and start that problem using the information we know about the pH. We, of course, have our pH is equal to 3.20. If you remember that all of these equations are hanging out on your formula chart, then awesome. You can go grab the equation to figure out the concentration of hydrogen ions. You know that the concentration of hydrogen ions is equal to 10 to the power of the negative pH. So if you plug that value into your calculator here, you get 10, of course, to the power of negative 3.2 here. You should get this value. And you can put that into, let me redo this, get this back up here for y'all, negative 3.2. And then you can go ahead and get this into scientific notation if you so please by doing this. And so our answer here for our concentration is 6.31 times 10 to the negative 4 molarity, okay? So we know that the concentration of the hydrogen ion after hydrobromic acid has dissociated here is going to be this value. And so we're going to work backwards with our rice table here. I'm going to go ahead and write out rice there. And your reaction is going to be your dissociation equation, as we were doing on the previous problems. You know how to do that. HBr will dissociate into the hydrogen ion and the bromide ion. Again, please don't forget to include your charge and your states here for a correct dissociation equation. And this value here, this is our ending value for our hydrogen ion concentration. So we know at the end, once this has completely dissociated, we get this concentration of hydrogen ions, okay? And look at this, we have one hydrogen ion for every one bromide ion. So the ratio of hydrogen to bromide ions is 1 to 1. So we know that we're going to have the same concentration of bromide ions. And this was a strong acid. So we know that this completely dissociated at the end here. We know that we're not going to have any of this because it's all in the form of these ions now. Okay? And you're essentially just working backwards. Okay? We knew that before dissolving, these were going to be at 0. The change from 0 to this, okay, we added this value to get from 0 to here. Okay. And this also has a 1-to-1 ratio with all of these. Note, remember, there's basically an imaginary 1 in front of all of these, this formula, as well as these ions here. There's an imaginary 1. So we know that the ratio from this to this was 1 to 1. The ratio of this to this is also 1 to 1. So we knew that this had to have decreased by that same amount to get us this final concentration of 0. So we must have started with this concentration here, okay? And that is what we were asking for in the question, okay? We asked what was the molar concentration of the acid to start with. Well, remember that I stands for the initial, okay? So that is that right there. Should have the molar concentration of the acid to start with. So we basically we worked backwards with this rice table to figure that out. And that's a very simple one that you work backwards. Let's make it a little bit more complicated. Let's use a base instead, okay? So the next example we're going to do together, example 25 here, we are given the pH of a barium hydroxide solution. Okay, so barium hydroxide is this guy. And we know that pH is 10.4, which makes sense, it's a base. And we want to know what was the original molar concentration of this base. So same thing, we're going to have to work backwards, but this is in fact a base, and so, if we were to write out our rice table, and we were to write the dissolving equation for this guy, you would get the barium with a +2 charge, and then we have 2 hydroxide. This compound is made up of 1 barium ion for every 2 hydroxide. So I'm going to make sure I include that 2 as a coefficient over here in my dissociation equation. And so here we need to do some calculations with our pH to get our value here. We're trying to figure out this concentration of hydroxide because that is going to be the piece that allows us to work backwards to this original molar concentration of the base. So let's go ahead and take that pH that we know is 10.4, and we know that if we do pH plus POH, we can get a value of 14. And so in order to figure out the POH, so we can use this value to get our hydroxide ion concentration, we will do 14 minus our pH. 14 minus our pH should get us our POH. Again, I'm using this. pH plus POH equals 14. I'm just kind of rearranging that equation. That will give me a POH value of 3.60. And again, we know that we can calculate the hydroxide ion concentration. Remember that those brackets are just an abbreviation. It means concentration. The concentration of hydroxide ions is going to be equal to 10 to the value of the negative POH. Okay? And so if we do our value of 10 to the power of the negative POH, 3.6 here, we will get 2.51 times 10 to the negative 4 as our concentration. Okay? Okay, so 2.51 times 10 to the negative 4 molar is our concentration of the hydroxide ion. So let's go ahead and plug that in. Again, we were doing this whole calculation over here to try and figure out this value so we can work backwards. Okay, so we have 2 hydroxide ions for every 1 barium. So this is going to be a little bit trickier here because we don't have a 1-to-1 ratio. Of course, this is a strong base, so we know that at the end of the dissociation, all of this will have dissolved into barium and hydroxide ions. So we know that the ending concentration of barium hydroxide is 0. But here, we have a 1-to-2 ratio barium to hydroxide, or you could say that we have a 2-to-1 base ratio hydroxide to barium. So there's going to be double, the concentration here is going to be double what we have for the concentration of barium. Okay, so we're going to have to do this value divided by 2, which you should, if you divide that by 2, you'll get 1.26 times 10 to the negative 4. Again, remember that, we're increasing by 1.26 times 10 to the negative 4 because we start with a concentration of 0. Because we're assuming at the beginning, there's none of this present. This hasn't dissolved yet. But we had to add this to get here, okay? Remember, this is a 1-to-2 ratio, barium to hydroxide. The reason why these numbers are different is because this 2 over here, this coefficient, let me put a plus symbol there. For this coefficient, we had to do 2 times this value here in order to get the final 2.51 times 10 to the negative 4 concentration we've assigned to our hydroxide, okay? And so these have a 1-to-1 ratio. So this decrease is going to be the same value, just opposite, obviously, here, okay? So our initial concentration of barium hydroxide, you have to be careful, y'all, is in fact 1.26 times 10 to the negative 4 molarity, okay? If you didn't do the Rice table, you didn't see this difference in the coefficients here, the ratio that you did not see that the ratio was not 1-to-1. We in fact have a ratio of every one of these gives us 2 of these ions. You may have made the mistake and said that this was the initial molar concentration, but this is not. The initial molar concentration is 1.26 times 10 to the negative 4 molarity, okay? So important to do that Rice table, show your work, make sure you are not making any silly mistakes. And if you are still confused, please feel free to come to my tutorials to ask me questions. I know it's a little bit harder to just see the video and not get direct feedback, have those questions you can ask immediately. But I'm here for tutorials if you need me. And down here, if you want to try this problem as well, I can give you the initial concentration as well. Okay, that is your answer there, 0.0501 molar. So go ahead and give those other 3 problems that we did not do a try, as well as the ones on your practice worksheet. Those will help you. You just need to do the strong acid and strong base calculations. You don't need to do the weak acid, weak base calculations. Okay, hope that helped, and thanks for tuning in.